Okay, now we're going to talk about electric field and magnetic field in matter. So this topic is not the main focus of this module. I'm going to go through some properties that are related to electromagnetism for communication. So first we have conductor. So suppose we have external electrical field, and then if this is a perfect conductor, what will happen is all the positive charge will move immediately towards the direction of the external electrical field, and then all the negative charges they are left on the other side. So effectively, we have the external electrical field, and then we have the induced electrical field, and they cancel each other. So within the conductor, we have the electrical field equal to 0, and we have the volume charge density equal to 0. All the charges, they will reside at the surface. So we have the surface charge here. So another thing is, if you have like a cavity here, so there's free space inside of this cavity, then there will still be no electric field, because if you draw any loop inside of the conductor, we know the curl of E equals to 0. So closed loop integral equals to surface integral curl of E dA. So this is equal to 0. So if there's no electric field outside, there will be no electric field inside. So electric field, they don't penetrate a conductor. So for example, if you are sitting in your car and there is thunderstorm, you wouldn't get electrocuted. Okay, so that's a property. So how do we know how good a conductor is? So I have the conductivity. So for that, we have Ohm's law that tells us how good a conductor is. So basically, if we want current, we need push on the charge. So current equals to sigma conductivity, and then unit force per charge, the push on the charge here. So if the force is from electric field and magnetic field, we have conductivity and then electric field, and then V cross B, magnetic field. In reality, the electric field dominates. The magnetic field is really, really weak. So this is this approximates to conductivity and then electric field. So sigma C is conductivity of the medium. So if we have a perfect conductor, we would have sigma C conductivity equals to infinite. So little push and then you get infinite current. In reality, that doesn't happen. You have little push and then you get current. That's good enough. And then you also have insulator, where the conductivity equal to 0. So no matter how hard you push, you wouldn't get any current. So here's a past exam question, very simple one. So the question is, does it happen that maybe we have current, so current doesn't equal to 0, but we have electrical field equals to 0. Does it happen? Of course it happens. Like conductor, there's no external, there's no internal electrical field, but flow of charge will give you current. So how to see it from Ohm's law? So we have electrical field equals to current divided by conductivity. So if current doesn't equal to 0, but conductivity equals to infinite, then the electrical field equal to 0. So this is possible theoretically. Now we're going to talk about linear dielectric. So let's start with some basic atomic knowledge. There's this old joke: don't trust atoms. Why? They make up everything. Well, they do make up everything. Okay, so we have atom here. So we have nucleus that include, neutron and proton. Neutron has no charge and proton has positive charge. Ideally, we should have the same number of proton and electron. So electrons, they orbit around nucleus, around shells. So the number of protons determine a chemical property. So for example, the number of protons will define an element. So different elements that have different numbers of protons. And then the number of electrons will determine the chemical behavior. So if you have one electron missing, or if you have one more electron in here, then basically you have different kind of behavior. So you probably would learn from other modules that the most reliable structure is to have 8 electrons as the outermost shell. But many atoms, they don't have 8 electrons in their outermost shell, so they can form bond, so they can share their electrons, and then we can dope elements, to produce light and receive light. Anyway, so there's this another joke from American sitcom Big Bang Theory. It says that a neutron, a proton, and an electron, they walk into a bar, and then the neutron asks, how much for the drink? And then the bartender said, for you, no charge. Okay, anyway, so now we are going to look at linear dielectric. I hope that would help us to understand linear dielectric better. So basically we have external electric field. So if this is a conductor, we will have free charge moving and then to the surface, and then the induced field will cancel the electric field. So there is no electric field inside. But what happened to linear dielectric is that the positive charge will be pushed to move towards the same direction as the electric field, but it wouldn't go far because the attraction between positive charge and negative charge is too strong. It kind of stopped. So this structure is called electric dipole. And electric dipole means, charges are not free to move, so they introduce bond charge. So basically that gives us, accumulation of charge. So in this scenario, in this situation, Gauss' law still stands, but we need to modify it for linear dielectric, especially. So Gauss' law, we have the integral form, which is the flux of electric field is equal to the total charge enclosed divided by epsilon 0, which is permittivity of the free space. But now for linear dielectric, we need to modify this. This should equal to the total of free charge divided by the permittivity of the material. So this probably would be clearer in differential form. So here we have the divergence of the electric field. So originally, for the Gauss law, we have the total volume charge density divided by epsilon 0, but now this is changed to the total free charge density divided by epsilon. So the permittivity of the material. So basically, in the material, we have the total charge density still there, but it equal to the free charge and then bound charge. Yes. But we don't need to go that far away. Only thing that matters to us is Gauss law needs to be revised. So epsilon 0 here, epsilon. So for most materials, we have epsilon bigger than epsilon 0, that is a free space. So if I have perfect conductor, we have epsilon approach to infinite. Let's look at an example that would make it a lot clearer. So for example, we have a metal sphere in the middle. That's a metal sphere here, uniformly charged with Q total charge, and the radius is A. And then we have another layer of linear dielectric. The permittivity is epsilon, and the radius is B. So question is, what is the electric field? So first of all, inside of the metal is a conductor. Inside of the conductor, we have electric field equal to 0. So there will be, so free charge, they are free to move, and they reside at the surface. So inside of the conductor, electric field is always 0. And then second, so inside of the linear dielectric, so R is between A and B. How do we calculate electric field? We find Gaussian surface. So we find a Gaussian surface that's parallel to the metal surface. So we have 4 pi r square. That's here. Multiply E. So total area and electric field equals the total free charge enclosed. The total free charge is the charge in the metal. So we have Q. And then we have epsilon instead of epsilon 0. So we have, we have epsilon. So we have linear dielectric. So the electric field inside of the linear dielectric is, so we have E equals 4 pi epsilon r square Q, and direction is perpendicular to the surface. And now what happens to any point that outside the linear dielectric and also the metal? So R bigger than B, what happens? We have another Gaussian surface. That's outside of the linear dielectric. So now we have 4 pi r square E. So Gauss law, and this is equal to the total charge enclosed. And here it is outside of linear dielectric. So we have epsilon 0 again. So Q divided by epsilon 0. So I have E equals Q divided by 4 pi epsilon 0 r square r. So what we can see here is that epsilon is bigger than epsilon 0. So this field here inside of linear dielectric is smaller than the field in the free space. Ideally, if the linear dielectric is a conductor, if it's replaced by conductor, we have epsilon approach to infinite, then here, then the E field equal to 0, the same as inside of the metal. So dielectric kind of try to reduce the electric field, but it cannot do all the job because electric dipole here, because the attraction between electron and proton is still very strong. They are not free to move. So there is bound charge and there is accumulation of charge. Is there a relationship here? So we have perfect conductor, permittivity equal to infinite. And then earlier we have Ohm's law that tells us conductivity would become infinite if it's perfect conductor. So there is a relationship between conductivity and permittivity. The relationship depends on carrier frequency though. Another observation here is that conductor, dielectric, and free space, none of them is useless. They all have different roles. For conductor, we have electrons moving free. They are all free to move. So we don't have electric field. We don't have electric field, but we have current. And then for dielectric and free space, we don't have free charges just flying about. We don't have free charges in the air, but they can convey electric field. You see, the electric field, they would degrade at the rate of 1 by r squared, but still there's electric field going out. So this is amazing because dielectric and free space, they can convey electric magnetic wave. So what is fiber? Fiber use glass to convey light. What is glass? Glass is insulator. And then wireless communication network use free space to convey your mobile phone signal. So yeah, minor correction here. So here we have, this is unit vector because the magnitude is already taken care of by this magnitudes, and this is unit vector. So what happens when we have external magnetic field applied to a material? So let's still look at magnetic field in comparison to electric field. So we know there's, for linear dielectric, we have electric dipole, where when we have the external electric field, the positive charge would be tempted to move towards the same direction as electric field, but it wouldn't go far because the mutual attraction here is too strong. The mutual attraction between protons and the electrons are too strong. So this create bound charge, and we need a modified Gauss law. So this basically reduce the electric field, but it cannot completely make electric field equal to 0 like a conductor. So what happens to the magnetic is there magnetic dipole? So before Ampere's time, people used to think there is a north pole and south pole, and so when we apply external magnetic field, then there will be north pole and south pole created. So here we have a magnetic dipole. This is in microscope. It's not the north pole and south pole of the Earth. So this is called Gilbert model. However, this model is wrong. So Ampere found out that magnetic field is always generated by current. Why this is wrong? So we know that the divergence of E equals to volume charge density divided by epsilon 0. And then we know the divergence of magnetic field always equal to 0. So there's no magnetic charge. So if magnetic dipole look like this, then we separate north pole and south pole. Each one of them in their own space will be magnetic charge, but there's no magnetic charge. This model is completely wrong. So what does magnetic dipole look like? Magnetic dipole doesn't look like this anymore, doesn't look like this anymore. It is tiny current loop. So when we have an external magnetic field, the material will generate tiny current loop. That is magnetic dipole. So if the tiny current loop is generated in a way that the induced magnetic field is the direction of the induced magnetic field is the same direction of the external magnetic field, we call it paramagnet. So if we apply external magnetic field, and then we have magnetic dipole, which is tiny current loop. That's opposite direction. Opposite direction for the induced magnetic field. We call it diamagnet. There's a third kind which can memorize magnetic field, which is called ferromagnet. Iron is like this. So they have a lot of magnetic dipoles. They are very stubborn, so they try to align with their neighbors. So when you apply magnetic field, unless you have the magnetic field so strong that makes them all change, otherwise they wouldn't change. So what happens is like this. So you have current. So when you don't have current equal to 0, and then you increase the amount of current, you have induced magnetic field like this, and then it go to saturation point. And then when you reduce the current, the magnetic field would be also reduced. But when the current is reduced to 0, magnetic field wouldn't reduce to 0 because the tiny current loops, they are still trying to align with their neighbors. So magnetic field is memorized. Here, this point at current equals to 0 is permanent magnet. And then if you increase the current towards the other direction, the magnetic field would reduce to 0. And then if you further increase current towards the other direction, the magnetic field would increase, but then go to saturation again here, saturation again at this point. And now if you reduce the amount of current, magnetic field would be reduced. But when current equal to 0, magnetic field wouldn't be 0. This is another permanent magnet point. And now if you further increase the current, the positive current, then it would go here. So it would be like this. So ferromagnet is never linear. We care more about these two cases where we can have linear media. So what happens in linear media? Linear medium. So we still have Ampere's law, but Ampere's law needs to be modified. So initially, the integral form, we have closed loop magnetic field equals to mu0 and then total current enclosed. But now in linear medium, so it's not free space anymore. We have mu and then I enclosed free, so free current enclosed. Because here what happens basically is you generate this mini small, tiny current loop, and this would generate bound current, and this would do something to the medium. So basically, if we have paramagnetic, the current density would be increased. If we have diamagnet, the bound current would be against, the initial current density. So the current density would be reduced. But here, this is equal to the free current. And then the differential form, we have the curl of magnetic field equals to mu0 and then J, the current density, free current density. So we still have the total current. Total current equals to the free current and then bound current. Okay. So we don't want to get into too much detail into them. We only need to use Ampere's law differently. So let's try to understand this better with an example of linear medium. So this is example 6.3 of the textbook. So basically, if we have solenoid, we have current in, and then the wire would surround this. The current is I, and another parameter is we wired the current with n times per unit length. So now, based on right-hand rule, we know the magnetic field is inside and going up. So now what we need to do is we need to find, Ampere loop. There is no magnetic field outside. There is magnetic field inside along this path. If the length of the Amperian loop is L, then we have here modified Ampere's law. We have BL equals to mu here, and then total current enclosed, free current. Free current is what we put there. So we have mu NLI. So L can be deleted. So basically B equals mu NI. And if the up direction is Z direction, we have Z here. So if it's free space, we have mu0. So here mu, when mu is bigger than mu0, we have the magnetic field enhanced. So we have paramagnet. So if we have mu smaller than mu0, we have the magnetic field reduced. So we have diamagnet. One last thing about electric field and magnetic field in matter is Maxwell's equations in matter. It's actually quite straightforward, but it's a really nice exercise on Maxwell's equations. So first of all, the classic one, we have free space. So for free space, we have epsilon 0 and mu 0. So the permittivity of the free space and the permeability of the free space. So in general, epsilon indicate how electric field interacts with material, and mu permeability indicate how magnetic field interact with material. So the classic Maxwell's equation is for free space. So we have Gauss law. In free space, we have Gauss law, which is the integral form is the flux the closed surface integral of the electric field equal to the total charge enclosed divided by epsilon 0. And this also has a differential form, which is the divergence of the electric field equals to the total charge density divided by epsilon 0. Okay, and then we have Ampere's law for magnetic field. The integral form, we have the closed line integral on the magnetic field. So this equals to mu 0 and then total current enclosed. And the differential form, we have the curl of magnetic field equal to mu 0 and then current density. So now the classic Maxwell's equations. It gives us, first of all, the divergence of the electric field equal to the charge density rho divided by epsilon 0. So Gauss' law gives us this. And then the second one is the divergence of magnetic field equal to 0. No one directly named this, no one directly claimed this, but you can calculate this from Biot-Savart law. And then the third one is the curl of electric field equals minus dB dt. So this is given to us by Faraday. And then the fourth one was the curl of magnetic field. This is equal to mu 0 current density, and then epsilon 0 mu 0 dE dt. So this is given to us by Ampere's law. This is given to us by Maxwell. So that's a free space summary. And now if I have a linear medium, then we have epsilon and mu. They are not equal to epsilon 0 and mu 0 anymore. So we also need to modify Gauss' law and Ampere's law as well. So Gauss' law is modified to be the closed surface integral equal to total free charge enclosed divided by epsilon. And then the differential form is the divergence equal to the free charge density divided by epsilon. And then we have modified Ampere's law, which is a closed path integral of the magnetic field equals to mu and then I free current enclosed. And then we have the differential form, which is the curl of magnetic field. This is equal to mu and then the free current density. So basically you need to replace epsilon 0 mu 0 by epsilon and mu, and then you need to replace the charge and the current density by free charge and free current density. Okay, so now Maxwell's equations. We have, first of all, we have the divergence. It's now equal to free charge equal to 0. Divided by epsilon. And then the second one is the same. The divergence of magnetic field is still equal to 0. And then third is the curl of E, the same, minus dB dt. And the fourth, we'll need modification, which is curl of B equals mu and then J free. So the free current density, and then epsilon mu dE dt. So so this looks very straightforward, but this is actually very important because we have electromagnetic wave from free space to a medium. Or from one medium to another medium, there will be reflection, there will be refract transmission. So we will have epsilon 1 mu 1 here, and we'll have epsilon 2 mu 2 here. So when the field crosses a boundary, there will be discontinuity. So the field will not be continuous. The magnitude and the direction, there will be changes. So that is taken care of by boundary condition, which we'll learn just next. So for this boundary, on one side we have Maxwell equation here, and then on the other side we have another Maxwell equation. So this is still kind of important, but it will make more sense when we study boundary condition.